Learning Objective 9.1c, we're going to graph and determine domain and range of nth root functions. The easiest way to first determine domain and range is to actually do the sketch. So put this in your graphing calculator. Be careful that this negative sign is not typed as a subtraction symbol. When you do that, here's a rough sketch. You'll get a square root looking function like this. Now remember the domain and the range. The domain is going to be related to the x's, so just travel along the x-axis. As you travel along the x-axis, you don't see any activity start until you hit the number 1. You have to see if 1 works. If you put 1 in here, it would be 9 times 1 minus 9, so that would be 0. You can take the square root of 0. So for this, the domain is going to be all the x's greater than or equal to 1. The range is then going to be with the y's, so travel along the y-axis. There's no y activity until we hit this number here, which is -2. So then, therefore, the y's are going to be all numbers greater than or equal to -2. The next graph is a cube root function. One thing when you put this in your graphing calculator, you can either go to Math Num and find the cube root symbol, or just remember you can write this as x plus 2 all to the power of 1/3. It would therefore be -1 on the outside, and don't forget the 3/5 in front of it. So you can either type it with this radical symbol or change the radical symbol to a rational exponent. When you do that, here's what the graph looks like. Here's the picture of the cube root function. Now again, let's determine the domain with the x's and the range with the y's. As we travel along the x-axis, there's always graph activity. So in this case, I'm going to say that the x's are the element of all real numbers. If you travel along the y-axis, again, it doesn't look like there's activity down here, but be careful. This function continues this direction and it continues this direction. It's going to take a while, but this thing will actually gradually crawl up and this will gradually crawl down. Therefore, the range is we will have y activity down here at some time, and we will have y activity here. So for the y values or the range, again, it's going to be an element of all real numbers. Be careful with a cube root function. You might be tempted to think you can't have a negative underneath this radical, but you can. You can take the cube root of a negative number. However, if it was a square root, you could not take the square root of a negative. So when you go back to the original problem we first looked at, the reason why here that the x values had to be greater than 1 is if you put a number in here that is less than 1, you're going to start getting negative numbers under the square root, which is a problem. However, on cube roots, it's not a problem with negatives underneath the radical. 9.2a wants us to evaluate powers using properties of rational exponents without using a calculator. So the first thing you want to remember is when you have an exponent on the outside and various things on the inside, this exponent gets distributed to everything. So it actually has to touch the a and the 49. So this is going to look like 49 to the 3/2 power, and then it's going to be a in 6 times the 3/2 power. To simplify this, let's first look at the a value. Here you're just going to multiply a whole number and a fraction. I can make 6 a fraction by putting it over 1. Multiply, go straight across. This would become 18 over 2, which actually simplifies to 9. So I'm going to put its a to the 9th power. Now on here, 49 to the 3/2, you need to be able to simplify. So what you're going to want to do is take the 3/2 power and remember break it into two things. You're going to cube something and then you're going to take the square root or the 1/2 power. You pick and choose if you want to cube first or take the square root. With this right here, it's going to be easier to first come in and say you're going to do 49, do the 1/2 power first, and then after that you'll come in and cube it. The 1/2 power just means the square root. The square root of 49 is 7. So this actually becomes, it'll be 7 cubed, a to the 9th. You can simplify 7 cubed. It becomes 343, a to the 9th power is our final answer. 9.3a, we're going to rewrite logarithms as exponents and evaluate. This right here just says rewrite each in exponential format. We won't actually have to evaluate, but remember what to do. The base of an exponent is the base of the logarithm. The base of this logarithm is 64. So the easiest way to do it is kind of doing that swoosh. You always start with the base and then you swoosh around and bring it together. So when we do that, we're going to get 64 to the 1/3 power equals 4. So the exponent's base is 64, the exponent is 1/3, and it equals 4. Really, if you look at it, what this says is take the cube root of 64. What number 3 times is 64? The answer is 4. This is a correct logarithm. Let's do this logarithm. It's log base 16 of 256 equals 2. Let's rewrite it as an exponent. So remember, take the base of the log, which is 16, which becomes the base of the exponent. So it's going to be an exponent to the base 16. And I'm just going to take this, again, I'm going to do the swoosh around. So it's going to be 16 to the 2nd power is 256. And if you write that out, it'll look like 16 squared is equal to 256. This right here is actually correct. If you take 16 squared, you get 256. 9.3c and 9.6a are similar. Solve exponential equations by rewriting as logs and evaluating. Here they just want you to say is rewrite each equation in logarithmic form. We don't actually have to evaluate this one. So what we're going to do for these two problems is reverse what we just did up here. So if you look at it, this base of this exponent is 17. So that means it's going to be log base 17. To write it, just do that swoosh again. So it's exponent 17, so it's log base 17 of x equals y. So if you go this swoosh around, it might help you write it. What you're therefore going to have is log base 17 of x equals y. And that's what the logarithm would look like. The next one here works the same way. When you look at the exponent, its base is 1/16. Therefore, we're going to start to this base of this, so it'll be log base 1/16 of this value equals 2. So if we write that, it would say log base 1/16, so make that small. It's going to be of 1 over 256 equals the value of 2. If we were to come in here and take 1/16 and square it, we would actually get this value. This is what it looks like written as a logarithm. The next two want us to solve each equation. These are exponential equations. Whenever you have an exponential equation and you have to solve for the exponent, the only way to get that exponent down on the main base level is to rewrite it as a logarithm. So let's just apply those properties. If this is exponent base 8, it's going to become log base 8 of 9 equals n. So let's write that. Log base 8 of 9 equals n. Now be careful, they do want us to round the answer to the nearest tenth. If I just go back to the exponent, it says 8 to what power equals 9? Well, 8 to the first power is 8. 8 to the squared is 64. So I know the answer is going to be a little bit over 1. Now the easiest way to do that is not guess and check, but to rewrite it as this logarithm, and then just use our base 10 conversion rules. Remember, we can type this in the calculator. We use the log button, but be careful, the log button on the calculator is only log base 10. This is base 8. So to do the conversion, all you do is the log of 9 divided by the log of 8. So you're going to type log of 9 over the log of 8. This here indicates the base 10 button on the calculator. Always take the log of the physically bigger written number and then the log over the base number on the bottom. When you do that, you're going to get approximately 1.06. That should make logical sense since we thought it was going to be a little bit over 1. Number 9 works the same way, but this is base e. So what I'm going to write here is just do my swoosh. This is exponent base e, so it'll be log base e of 68 equals x. So when you write that, it would look like this. Log base e of 68 equals x. Now be careful, you may not write log base e. Log base e is the same as our natural log button, so it really just means the natural log of 68 equals x. All you have to do now is go to your calculator, hit the natural log of 68, and when you do that, you're going to get, when you round, they want to the nearest 10,000ths. So you're going to notice back on the first problem, I went to the tenths to the hundredths. I should have went out more. The 10,000ths, if that's tens, hundredths, I'd have to go thousands and 10,000ths. So that means 4 decimal places. So let's round this answer to 4 decimal places. That would be about 4.214 4.95 is our appropriate answer. And to get the rounding proper, let's go back to this first one. That would have rounded to 1.0566 to the 10,000th decimal place. Let's do some more solve the equation and again round to the nearest 10,000ths. So that's the 4th decimal place. Now when we have an exponential equation, again the variable is the exponent. In order to get the exponent by itself, you must rewrite it as a logarithm. But before you rewrite it as a logarithm, this entire power must be isolated. So what we have to do is get rid of the minus 7. So to do that, all we have to do is add 7 to both sides, which will therefore give us 2 to the 3x power equals 95. Now the exponent is all isolated. Let's just rewrite it as a logarithm. So it's exponent base 2, so it's log base 2 of 95 equals 3x. So just write that, log base 2 of 95 equals 3x. Now to solve this, what we want to do is put this in the calculator. Let's convert it. Let's do log of 95 over log of 2. So I'll do log of 95 divided by the log of 2, and that's equal to 3x. Once you do that, you're going to get 6.56986 equals 3x. Wrap this up by getting x by itself, so divide everything by 3 on both sides. And after you do that, you're going to end up getting the answer to the 4th decimal place, be careful, is going to equal, it's 2.1900 is what it's going to have to properly round to the 4th decimal place. This next one's the same way. The variable is the exponent, so we want to get 11 to the n minus 1 power by itself, so we have to get rid of the 6. To get rid of the 6, let's just come in and minus 6 from both sides. That's going to leave us with 11 to the n minus 1 equals 45. When we rewrite this as a logarithm, it'll be log base 11 of 45 equals this value. So let's do log base 11 of 45 equals n minus 1. Let's now do the log of 45 over the log of 11 in the calculator, and it's equal to m minus 1. When you do that, you're going to get 1.5875 equals m minus 1. Let's solve for m. To do that, we're just going to add 1 to both sides. Therefore, m in this case is going to be 2.5875 as our final answer. 9.3d wants us to solve equations by rewriting as exponents and evaluating. So when you have logs, we just reverse everything. A log equation, the easiest way to do it is you write it as an exponent. But sometimes you don't have to do that. Now, you're going to notice this first problem here. It's one log set equal to another log. When that's the case, there's a very nice trick. The logs actually just cancel out. So really all we have is an algebraic equation of negative 4n minus 7 equals 1 minus 3n. Now let's just go ahead and get our variables together. I'm going to move negative 4n over to this side. So therefore I'm going to add 4n to both sides. That's going to leave us with negative 7 equals 1 plus n. Let's subtract 1 from both sides, giving us n as an answer of negative 8. Now this second problem here doesn't actually work like the first one. This is 2 logs set equal to 1 log. Now I can't go ahead and start crossing off the logs. It can only be 1 log and 1 log. However, I can use my property of logarithms. When I have this log and this log being subtracted, what that really means is division. So what I'm going to do is come on in and condense these 2 logarithms together. So what's going to look like is this. It'll be log base 8 of 3x divided by 5 equals log base 8 of 12. Now what I've done is I have 1 log set equal to another log, so I can use the same trick I did over here. In this case, the logarithms cross out, so what I'm left with now is the equation 3x over 5 equals 12. To solve for x, let's multiply both sides by 5. When we do that, we're therefore going to get 3x equals 60. Now divide by 3 on both sides, And now we get that x is equal to 20. And that's our final answer. Looking at this next one, what we have is two logarithms set equal to a number. So again, what I want to do now, the only logical thing that would seem to do is try to get it to become one logarithm. So I can condense these two logarithms together. When logarithms are added, they can be crunched together into multiplication. So this becomes log. By the way, this is base 10 because it's not listed. So it's log base 10 of 7x equals 2. Now I can't come in and cross off logs because this is one log just set equal to a number. It has to be a log to a log. So when you're stuck with this, your only other option is it's simplified as much as it can as a logarithm. So why don't you go ahead and rewrite it as an exponent. Now I am going to come on in here and put that it's base 10 so I see that. Now when I rewrite this as an exponent, remember it's log base 10. I would do my swoosh around. So log base 10 means it's going to be exponent base 10. So I'm going to do 10 to the second power equals this. So I'm going to write it as 10 squared equals 7x. 10 squared is just 100 equals 7x. To get x by itself, let's divide both sides by 7. And now we're going to get, again, rounding to the nearest 10 thousandths, so 4 decimal places. I'll write x right here. The answer is going to be 14.2857. And we're done. Looking at this next one again, we have two logs on one side set equal to a various number. The best thing to do is condense down these two together. It's separated now as subtraction, which means we're going to divide. So when we bring this together, it becomes log base 4, and it's x squared plus 8. It's going to be all over 6 equals 3. Again, I can't cross off logs because there's not one over here. The only thing I can do is rewrite it as an exponent. So it's going to become 4 to the third power equals this value here. When we rewrite that, it looks like this. 4 cubed equals x squared plus 8 divided by 6. Now I'm going to do two things here. I'm going to actually go in and do 4 cubed. 4 cubed is 64. At the same time, I'm going to try to isolate x, so I have to get rid of the squared, the 8, and the divided by 6. So I'm going to get rid of divided by 6 by multiplying this side by 6. So let's go ahead and do 4 cubed, which is 64, and times it by 6. When you do that, you're going to get 384, and then it's equal to x squared plus 8. Let's wrap this up by subtracting 8 from both sides, which will give us 376 equals x squared. Now to solve this, all I have to do is take the square root. When I take the square root, x is going to equal to, be careful, it's plus or minus, and then the square root of 376 actually rounds to, let's do 19.39 to 2 decimal places there. 9.3e and 9.4c want us to understand logs and exponential graphs and their inverses, state domains, ranges, and asymptotes, and also graph base e exponents and find and graph inverses. So this first one here is let's find the inverse of each function. Here we have, they want us to find an inverse of a logarithm. Here they want us to find the inverse of an exponent. So remember, to find inverse functions, what you want to do is first flip-flop the x and the y. So for this problem here, the y will become x and the x will become y. So it's going to look like this, x equals log. I'm going to put that that's base 10, by the way, so I can see it, 5 to the y power. Now to solve this, I have to get y by itself, which is the exponent. So the easiest way to probably do this is to either use property of logarithms or to come on in and let's try rewriting the logarithm as an exponent. Here's the first method I would try. Is if this is log base 10, let's do exponent base 10 to that power equals this. So that would be 10 to the x power equals 5 to the y power. Now when you look at that, you still have to get y by itself, so it's a little bit tricky. In this case, y is still the exponent, so you're not really sure how to get that down to the lower level other than doing a logarithm. So I'm actually going to reverse what I just did, and I'm going to take this and actually rewrite this exponent as a log. So if this is exponent base 5, it's log base 5 of this equals y. So watch this, it becomes log base 5 of 10 to the x power equals y, and that would be an appropriate answer. Now there is another answer you could have gotten for this one, and I'm going to show you. I'm going to come back up here and keep it as a logarithm at first and use property of logs. This right here, this y, actually can become a number in front of the logarithm. That exponent can be carried down. So I'm going to take this and carry it down to the front and show you this. It would be x equals y log of 10 to the 5th power. Now to get y by itself, all you'd have to do is get rid of log base 10 of 5, and what you would do is you would divide both sides by that value. So here I would write log base 10 of 5 and log base 10 of 5. What happens, you're going to notice these would cross out. So now what you're left with in this format would be y equals x divided by log base 10 of 5. Now I will tell you this answer right here is actually considered equivalent to what's written here in the red. If I were to do some more math, and we don't need to touch on how you would necessarily do this, but I'll show you if you want to see why these are the same. Here's what happens. To get this logarithm out of the bottom here, what this really means is I can do log of 5 over log of 10. So I can take this side and actually rewrite it like that. Now what they're going to do is get rid of this fraction within a fraction. When you multiply it by its reciprocal, you would do log of 10 over log of 5. And the same thing over here, log of 10 over log of 5. So what you'd have is y equals x times the log of 10 over the log of 5. Now what this becomes is this is really log base 5 of 10. So watch this. This is kind of interesting. It goes y equals x log 5 to the 10. Now what they're going to do is actually bring this x up, and they're going to get the answer will be written as y equals log base 5 of 10 to the x power. And that is actually the same answer we just got here. So what you need to know is this. For on the test, you can either go this route and get this answer, or you could go this route, and I would be okay if you stop here. Technically, it's not simplified because a logarithm can be written as a fraction within this fraction. But I wanted you to understand this truly is the same as this answer if I were to go and simplify further. This part here would not be required. Let's look at the next one. They want us to find the inverse of an exponent. So again, all we first need to do to find an inverse is flip-flop the x and the y. So when we do that, we're going to get x equals 3e to the y power. Now this one's going to be easier to solve. To get y by itself as an exponent, we do want to rewrite it as a logarithm. But before I do that, I want to move the 3 because this is the whole power. To move the 3, let's just come on in here and just divide by 3 on both sides. So it'll be x divided by 3 equals e to the y power. Now to rewrite this exponent as a logarithm, it's going to be log base e of x divided by 3 equals y. Now before I do that, log base e is just the natural log. So I'm going to go ahead and just say the natural log right up front, and it's going to be of x divided by 3 equals y, and that's the appropriate answer. This second one here was much more simple to solve than this first one, which was a bit trickier. The next two here want us to identify the domain and range of each and to sketch it. So remember to type these into the graphing calculator. Here this is log base 3. That log button in the calc is only base 10. So what you'd have to write is log of x divided minus 1, then divided by the log of the number 3. So put that in the graphing calculator, and here's what you're going to get. It is going to look something like this. Now be very careful. In the graphing calculator, what's happening is this function's hitting an asymptote. So there's an asymptote here at x equals 1. So on the calculator, what you might see on yours is you might not see this activity in the lower end. It's because the calculator can't graph it. You need to be smart enough and realize it doesn't just stop here, it does continue on. Because logarithms and exponential functions are inverses of each other, an exponential function typically goes like this, therefore a log must also continue on. So here we have the actual graph. Let's talk domain and range. Our domain is our x's, the range is the y. If you look along the x-axis, we don't have activity until after 1. So be careful on here. The domain is the x's greater than 1. It can't equal 1 because it's an asymptote. The range on this one, the y's, there's graph activity all the way. So the y's are the elements of all the reals. Nothing's off limits for the range. Let's look at the next one. This is a natural log function, so we can just use the natural log button and graph it. Let's go ahead and graph exactly what we see using the natural log button. Now again, be careful when you graph it in the calculator, they tend to stop about right here. This graph does continue on. It is hitting another asymptote because logs have asymptotes. It's right there at x equals 2 is our asymptote. Now the domain and range for this, if we look at it here, the x's and the y's. The x activity doesn't start until after we get over the number 2. So here the domain is everything greater than 2. The range on this is like the other one, all real numbers. I just have to caution you again about the graphs of these. Don't cut them off here like it looks like on the calculator. If you do, you will not get full credit. 9.4a wants us to compute values using the compound interest formula. Remember that formula was y equals our starting amount, and then it's 1 plus or minus your rate over how many times a year over your time period times how many times per year. So if we read this problem, we deposit $5,000 at 4.35% interest, compounded monthly. So that monthly right now is our time period per year, so n is 12. By the way, the rate is 4.35%. The $5,000 is going to be your starting amount on that. And they want us to find out how much after 13 years. So that 13 years is our t. All we have to do is plug this into the formula. But be careful when you do that. So our ending amount is going to be y. We start with 5,000. This is 1 plus because we're growing. The rate, be careful, is 0.0435. Now, this rate here is an annual rate, but it's compounded monthly. That's why they divide by how many times per year. So divide that by 12. And then for the exponent, it's over 13 years, so you do 13. But be careful, they're going to compound it monthly, so 12 times every of the 13 years. So you have to times this again by the n, which they show right here, which is our 12. Now to simplify this, PEMDAS does apply. Do this rate divided by 12 first and then add 1 to it. And then you're going to raise it to this power. So it would first simplify to this value in the parentheses to the 156th power. Now do your exponents next and then multiply it by 5,000. Once you do that, here's what you get. You're going to have $8,792.64. Now 9.4b and 9.6d wants us to compute values using the continuous change formula. Remember that's a pert. So this is the ending amount right here is a, and that's going to be equal to your p, which is your starting amount, and it's e raised to the rt power. So on this one, we're going to deposit $5,000. That's going to be our p, our starting amount. The rate is still going to be 4.35%. And it's compounded continuously, so we use this formula, over 13 years, so that's the t. So all we have to do is to plug in these three values into this equation and solve. When we do that, our ending amount is going to be equal to a, is equal to 5,000 as our start, e, be careful about the rate, 0.0435, and this is to the 13. So I'm going to take e to this multiple of these two values, and when you do that, you're going to get it's 5,000. You're going to get times 1.760327. Now times that by the 5,000, And on this one, you're going to come back with $8,801.64. Do notice this problem and this was very similar. This was compounded continuously. This was monthly. Continuously, we got a few more bucks. It's not that different, but it is a little bit more money because they're hitting that artificial button continuously versus 12 times a year. Now, the other learning objective was to write an exponential continuous change model and solve. That's what the second problem is related to. Here it is. If a pile of leaves decays at a rate of 0.07% per day, how many leaves will be in the pile after 60 days, given you start with 2 pounds of leaves? And they want us to use this APERT formula right here. So let's just kind of look at the values. Again, they want us to know how many leaves will be in the pile after. So they want us to find P of T, and it's after 60 days. So in this case, our P of O is our starting amount. So here we're starting with 2 pounds of leaves. The rate we're doing is 0.7%. Be careful as a decimal. 0.007 is going to be that. You also have to be careful with this rate because if you look at it, it's decaying. So this is not growing by that, but it's decaying. So in that case, the rate has to be a negative value. So let's just actually start by putting a few of those things in the formula, and then we'll get to the time period. So for the formula, it's going to be the P of after 60 days is equal to, we start with 2 pounds, and then it's E to the negative 0.007. Now let's talk about what T would be. T can be a little tricky. Be careful. The first day is T of 0. So the 60th day on this one would have to be T of 59. However, we want to know after 60 days. So this represents on 60 days. So after 60 days means we would have to adjust this to be the number 60. So let's go ahead and put 60 into here. Now I'm going to simplify. Let's do this first. We'll then get, it's going to be equal to 2 times, this is 0.65705. Now if you times that by 2, what you're going to get is equal to 1.314 pounds. Now be careful on this problem. One of the things you're probably going to miss out on at first is putting the negative for the rate. But be logical. If you kept this at positive 0.007, this answer here would have been greater than 2, and it would not have made sense to you. So you would have to think about how you would adjust it. So before you circle the final answer, make sure it's logical. If it's not, adjust this problem. The negative rate would have helped you with that one. Also be very thoughtful on the wording. This is the trouble. One of the other tricky parts is how many time periods it is. 9.5a wants us to expand logarithms and simplify applying log properties. Right here, we just want to expand them. So let's go ahead and do these 4 problems. This first one here is to pull it apart. Now, the first thing I want to do before expansion is let's go ahead and actually take this little 6 and distribute it to both of these pieces. So I'm going to give this the 6 and that the 6. So log base 6. This becomes x to the 6th over y, be careful, to the 12th. Now I can expand. Division becomes subtraction. So this is log of 6 of x to the 6th minus log of 6 y to the 12th. Remember, we don't keep exponents there. We always do bring those back down. So those exponents are going to come down into the front. So the final answer is 6 log base 6 of x minus 12 log base 6 of y, and this is considered fully expanded. I'm going to go to 14 next. Now 14, you almost want to take this radical and rewrite it as a rational exponent. The cube root just means the 1/3 power. So this is really log of u v w to the 1/3 power. Again, don't forget this exponent would go to everything. So really what we have is log of u to the 1/3, and then we have v to the 1/3, and then w to the 1/3. Now let's go ahead and pull apart multiplication into addition. So log u to the 1/3 plus log v to the 1/3 plus log w to the 1/3. We're then going to wrap it up by bringing the exponents forward, and our final answer is 1/3 log of u plus 1/3 log of v plus 1/3 log of w. And this is considered fully expanded. The next one here, let's go ahead again and do this for property of exponents. Bring the forward the x and the y both. When you do that, this is multiplication. So this is really log of x to the 4th, and be careful, it is y to the 12th. Now we can go ahead and pull multiplication apart into log x to the 4th plus log y to the 12th. We're going to wrap it up by bringing those exponents forward and get a final answer of 4 log of x plus 12 log of y. And that's our answer. This last one here is going to be similar to up here. Let's go ahead and first make that radical and a rational exponent. So this is really log base 8, and this is c, and then it's a and b are to the 1/3 power. I'm going to go ahead and recognize that those both get that exponent. So let's write it as log of 8, c. We're going to do a to the 1/3 and b to the 1/3. Now let's pull the multiplication apart into addition. So that'll give us log base 8 of c plus log base 8 of a to the 1/3 plus log base 8 of b to the 1/3. We can come on in and bring these exponents forward. When we do that, it's going to be log base 8 of c plus 1/3 log base 8 of a plus 1/3 log base 8 of b. And this here is our final fully expanded answer. Now 9.5c and 9.6b condense logarithms and simplify properties of logs, and just simplify log expressions and equations or both. So now we're going to reverse what we just did and the last two problems here. So this logarithm here needs to be condensed into one log. I have 3 of them. First thing you want to do is go backwards. Let's go ahead and bring any numbers up into exponents. So the 2 comes up and the 5 comes up. That'll give us log base 8 of u squared minus log base 8 of w minus log base 8 of 5 to the v to the 5th power. Now I'm going to come on in and actually combine these two into division. So this becomes log base 8 of u squared over w. And then I'm just going to keep this other part here for a second, v to the 5th. Now to combine this together, what I'm going to do is take this and divide this. So let me just show you one way you can write it is like this. Log base 8, this is going to be u squared over w. Now be careful, it would be divided by the v to the 5th power. So when I combine it, it looks like this. Now we have a complex fraction, so we have this over this. I can get rid of v to the 5th on the bottom and simplify. What I would do is just look like this, multiply by its reciprocal. So 1 over v to the 5th. And what happens then is when you clean this up, you get log base 8, it's u squared over w v to the 5th. That is the final answer. This one is a little bit tricky because it does 2 different sets of division. So depending your approach, you might find an easier way to get it simplified like this. But what I just showed you here is a nice clean way to do it, as long as you clean up this fraction down here and multiply by the reciprocal to get it to be a clean fraction and not a complex fraction. So this definitely is a tougher problem. Now the last one is a little bit more lighthearted. Let's go ahead and bring any of these coefficients forward into exponents. So the 3 comes back up and this 6 comes back up. That would give us log base 2 of 7 cubed plus log base 2 of 6 to the 6th plus log base 2 of 11 still. Now, I could bring this all together at once. I'm going to do it in 2 steps just to show you. I'm going to bring these two together. Addition becomes multiplication. So it's log base 2 of 7 cubed times 6 to the 6th. And that's plus log base 2 of 11. Now these two can be brought together into multiplication. It just comes down to log base 2. It's going to be 7 cubed times 6 to the 6th times 11. And this is actually considered our final answer. So you can see when you have addition and multiplication, it comes together very cleanly. Again, sometimes a subtraction into division can be a little bit more complicated. Just take your time and you can do it.